you very much. I'll try to give this in slide talk form, which is very unusual for myself, so I hope I don't screw it up completely. So I would like to try and motivate the whole thing with a formula that I suppose you all know very well, the Dirichlet class number formula. So as you recall, the class number formula somehow connects the arithmetic data that you have in a number field. And so you have on the one hand the units, important arithmetic information, the class group, and the dedicated zeta value, say at point 1, or by functional equation at point 0. Right? That's take Taylor expansion, and the first non-vanishing coefficient, in a sense, is given in this formula, zeta f star. So I think that's the simplest form. Zeta f star equals minus hf. And zeta f star at a point m is essentially take the limit s goes to that point, zeta f of s divided by s minus m to the corresponding power to which it vanishes. And then so we know for a number field that the vanishing order is R1 plus R2 minus 1, where R1 is the number of reals and R2 number of complex places. And then we have H times R divided by W, and these are the three objects. The first one is the order of the class group. So CLOF is here denoted as the class group. Then RF, the regulator, you can think of as a kind of co-volume of a lattice. And the lattice is given by coming from the units, OF star, and you take a function, the log absolute value. Well, you have to take all the Galois embeddings of that number field, and then you take the log absolute value. That's sort of the function that transports the units into a nice lattice. And then we divide because we overcount somehow, because roots of unity will give us a multiple count of things, so that's just a finite a little thing in the denominator, not too important. And so we'd like to see a higher analog of that. And any higher analog should have higher arithmetic data. So what do we call higher arithmetic data? So first higher units, higher class group, just in the same way as before, and well-dedicated zeta value at a higher integer, well, greater than 1, or by functional equation again at 1 minus m. And then we could ask for a formula that has a similar flavor, that zeta f at 1 minus m, is that a product in, say, the numerator of higher class group, CL sub m is now here the notation, ad hoc notation for a higher class group of OF. And we have a co-volume of, well, higher logs, or higher log absolute value kind of function, evaluated on higher units. And we fix the index m. So we have mth class group, mth higher units, and we divide out by the things we overcount. There should be something like mth higher roots of unity in our number ring. And then you see that there is an extra lambda, because you never can be sure, or you couldn't expect that to hold on the nose. So there will be some fudge factor or a missing factor, call it lambda for now or for this talk. Typically it's an explicit power of pi and times a rational number, but that's something to for the books later on. Now the right setting for this is what's called algebraic K groups of number rings. So think of that mainly as a black box. So it's just think they are abelian groups of finite rank for that purpose. For these number rings, it's always abelian groups of finite ranks, so it's not too frightening as such an object. And so I start with the second one first. K naught of OF, the zeroth such, is known to be essentially the class group up to a factor of z, which is not so important here. But so that really captures the torsion information on that class group. And K1 of OF represents the ring of integers, the units in that number ring. So already those two data, CLOF and OF cross, now have an interpretation in terms of K1. And then at the time, well, already like almost 40 years ago, Lichtenbaum asked for a formula of the following type. So you take zeta f star, so this first non-vanishing coefficient at 1 minus m, and it should be up to this missing factor lambda, a quotient of those groups K2m minus 2, that looks a bit maybe excessive with these indices, but so K2 minus 2, and you take the torsion and divide by the order of K2m minus 1, so the torsion group of that. So these two give you an important part of the information. And the crucial thing that needs interpretation is the one on the right-hand side. So this co-volume of the higher logarithm on higher units. And for the higher units, that would be K2m minus 1, so the odd-indexed K group, whatever that is. And the problem with that is, of course, that the definition of a K group is pretty abstract, and especially the higher ones are very hard to take in. And people have been trying, and that was Bloch in the late 70s, I think, when he came up with the first candidate for K3 of a ring. And that was, I think, the seminal work on which Zagier built on later on. And he found a candidate for higher odd index K groups. And these are now experimentally accessible. And that's what I'm trying to briefly indicate in the following. So what should be such a higher unit group? Let's do it for the case m equals 2. And so we need to understand, in principle, a subquotient of the free abelian group on that field. So it's just linear combinations of elements in F. And the crucial map that needs understanding is the following. So you go from from ZF, to F cross tensor F cross. So for simplicity, I take this target. There is a slightly more computationally convenient target. And then all you need to understand is the map sending a generator to generator x to x tensor 1 minus x. And what you want to, and then linearly extend it. And as a first not quite trivial example, let me give one of my favorites. I claim that we're interested in the kernel of this. And if you take minus 8, minus 6, yeah? No. Yeah? Make sense? Kind of? Right, so here I claim that this lies in the kernel of the map partial or partial sub 2 upper, even for f equals q. So that's sort of a thing that needs understanding. So that is here minus 8 tensor and 9. So that's 1 minus minus 8. Minus 6 times minus 2 tensor 1 minus minus 2 is 3. And now the point is that here you have, we work in F cross. So we look at the multiplicative structure of F, the multiplicative group. But then we somehow combine it with the additive one here with 1 minus. and all hell breaks loose. So that's here. The crucial point is that you combine both the multiplicative structure and the additive structure in this way, and suddenly you get quite unusual phenomena. And this is one of the simple phenomena. So for instance, you get, if you write -8, this is -2 to the power 3, and this is 3 to the power 2. So you're allowed to pull those exponents to the front individually. And therefore you get a 3 from here, a 2 from here, and that will cancel with that 6. So that's the reason why this lies in the kernel of that map. So that's sort of an important example to understand, to get a little feel for that map. That's so our key object is the kernel of this map. So that will be the higher units here of order m equals 2. And then for general m, you just thicken the one on the left. You just have more tensor factors of x on the left, like m minus 1 if your index is m. And that is the crucial map that needs understanding. Once you have that in place, once you have a good grip on that, you're in business here. And a good function on that kernel, and the one that we would be aiming for in that formula, would be a single-valued variant of the logarithm, the polylogarithm. So polylogarithm is just take power series of log 1 minus z, or minus log 1 minus z, and generalize it in a quite obvious way. Right? If m equals 1, then obviously that is the power series for log 1 minus x, and then for m in general, you can define it in the unit disk, and then you can extend it to the complex plane by an integral representation, which we don't need here. And this has been in not only that m logarithm, but already the single-valued variant, which is a good function, has been in Paris for decades. And this is our log sub m. So that's a function that should enter into this higher Dirichlet class number formula. And if we, the beautiful thing is, if we evaluate Lm on that kernel, that gives essentially a lattice. So here I'm throwing things under the carpet. So there's an inductive condition which is quite delicate, but let's just ignore it for the crucial understanding. It's not really important. So evaluating Lm on that kernel, that gives our lattice the corresponding thing as log absolute value gives on the units. That's and even more beautiful, the co-volume is related to the zeta value at 1 minus m. So everything's kind of in place.
All this is conjectural?
Not quite. So there are bits that have been proved for m equals 2, for instance, and for m equals 3. And for higher cases, as you well know, what's not conjectural is that that should give a lattice. So that is, and that's an important bit. But the co-volume bit.
Where is this lattice? What is
the
lattice
you think again? All the images under the, you have your field embedded all into C in all possible ways, and then you get your vectors on for same as for the log. Just replace log by log sub m, and then you get the right picture. Okay, and yeah, so that has been done already quite a while ago, at least in embryonal stage. So if the degree and discriminant are not excessive, then very often one gets a non-zero co-volume. And last night I tried again with all the new power that we have now with the new installed Paris, and it's great that there is this self Paris size max. It threw me out. Typically, I had different jobs for different ones, and I was always thrown out. Now I can run the thing that's immediate, and that's really beautiful. So if after many experiments you can formulate this combined. I didn't tell you what Zagier's conjecture precisely is, but it's roughly a qualitative version of this Dirichlet class number formula, but using, say, his approach to the K groups. So where Lichtenbaum still had these K groups in place, replace those by Zaghi's conjectural candidates for being as good as K groups. And then one can try to make those experiments in Paris. And for small m, at least m equals 3 or 4, I think I can make that missing factor precise, and for higher ones, not yet, unfortunately. What we also get is from the formula, just like you get information on the class group by doing unit calculations and comparing with the zeta value. You do something similar there, and you get sort of the left-hand side of our original formula. That was, so you can say it's zeta f star of 1 minus m that's the k2m minus 2 OF times this co-volume, whatever it was, divided by something simple, kind of. So we're aiming for this group, which typically is very hard to detect. And people, one doesn't have a good means to understand what these groups are. So using experiments, we can get a glimpse into those groups. And just, in most cases, small discriminant, degree up to, say, 8. We get mostly boring factors like powers of 2, powers of 3, just small ones. But okay, then eventually, or on and off, you find nice prime factors. For instance, here we have a field of signature for 1, and not too rather small discriminant, and a factor 79. And my favorite example is this, signature 2, 2, and a pretty small discriminant, 229 squared. There are 2 prime factors predicted from the program. The first one is okay, or already nice, but the second one is really the one that blew my mind, so I was really happy to see such a factor come up. Now, the problem with the whole thing is, it now works beautifully up to m equals 4, and for the first few ones in the number field table. But for m greater 4, very often one gets, with this approach, a rank which is not maximal, so the covolume doesn't really come out. So we cannot say much. So you try to run the same thing in many different ways with different parameters, and it's a very delicate thing because as soon as you go over the top, then Paris will unfortunately, or QFLLL is just, okay, QFLLL will just, not be able to finish within decent time.
So how does that work with the conjecture when the covolume is 0?
No, but you can't do it.
No, the covolume will be non-zero, but I find covolume experimentally. I find covolume 0. I don't have enough to generate the full lattice. Yeah. So you know what you expect, what the rank is for the lattice, but you just don't find enough generators. And so here, at least that's my current bottleneck. I'm sure that one can improve a lot on that.
You can do it entirely differently.
Ah, okay.
Not perfect.
Okay, yeah, great.
But if you don't know that you got the full lattice, how do you know that the factor 131 and so on is just
You get a bound from below. The thing is, you get the bound from below, not from above, and that's important. Once you find a factor, you still don't know what that K group is, but you get a lower bound on that order, and that's okay. Then we have also had proven results. So with Karim already 15 years back. So while all the previous ones are completely experimental, but still a nice glimpse. But here it's definitely proven using Paris. And hundreds of cases have been proved this way. And at the time, there were papers out for one of these individually, so one after the other. And so this was just covered then by his implementation. Yeah, so up to a handful of cases, we found all of those corroborated for imaginary quadratic fields, and but only K2. We have nothing for K4, unfortunately. And there, yeah, we don't care. There is still. Yeah, so and so I wanted to also advocate the use of multiple polylogarithms, which have been implemented recently by Henri in many cases. So there's a little issue with convergence close to 0.1, but that does not affect the multiple zeta values, which are the ones to come. So multiple polylogs is essentially you take it as if you took a product of these polylogs with those indices, except that you sum over that cone, which is ratified over there with K1 greater K2. So if K1 and K2 ran independently, then it would just be a product of Li M1 of the first variable times Li M2 of the second, but here we sum over a cone. And that suddenly gives you a larger class and actually a very useful class to deal with. And if you now specialize these zi's to 1, then so you just erase the numerator or replace it by 1, then what you get is a multiple zeta value, zeta M1 comma M2. And these are actually extremely interesting numbers. In many different contexts, you have them in knot theory. They occurred in Feynman integral calculations for physicists. In number theory, obviously, and they form an interesting kind of tapestry of numbers. So think, so it's in a sense a more extensive class than algebraic numbers. So algebraic numbers, you have your Galois theory. There you have presumably transcendental numbers. I mean, almost none of them is known to be transcendental, only powers of pi. But for instance, zeta 3 already, we only know that is irrational. But even for zeta 5, that is not even proved. So there's lots and lots unknown, but the picture that one has, you have lots and lots of interesting transcendental numbers with a beautiful group action in principle on it. So there's something like replacing the Galois group for algebraic numbers in this context as well. So the motivic Galois group, as some people call it. And so they are what's called a class of periods, so integrals defined over rational with rational coefficients over rational differential forms and over a domain that is given by say rational boundary conditions. And they have lots and lots of linear relations between them, and that's one of the beautiful features that one can find among them. And these have now been implemented under the name ZetaMult. So that is Henri with support from Karim. And I would advocate that as a wonderful playground for experiments. And it's really lots of fun. And what maybe just on the side is something that we've dealt with Don Zagier and Masanobu Kaneko, is that there is a relation with modular forms for those zeta values, multiple zeta values, which there seems to be nothing whatsoever modular about this, but still there is a relationship, and only for SL2Z, but still already that is maybe surprising, and it goes via so-called period polynomials. Maybe we can, if there is still time later on, one could try to see that the cusp form delta, so the first cusp form actually implies the following relation. This we can try to corroborate in principle, or you can try to corroborate in ZetaMult. So that is essentially what I wanted to say about the theoretical side, and maybe just to give an indication of a program that is working to an extent. So and which maybe Karim can help improve immensely. So what I tried to,
Can you make it bigger?
yeah, okay, like this.
A little more.
Even more?
Just yeah.
Okay, so let's take any not too big number field. So the function, just go, okay, very good. I shouldn't have done that. Oh, shit. Okay, so, okay, I'll try, I'll try it without. So I tried to suppress the printout in between, and I failed miserably. So now the function here tells me, at least in reasonable time, what I have as a conjecture for, say, K2 of this one. Now we can be a bit more. Sorry?
For this one with the theorem.
Yes. We might not even have done that. Okay, let's be 1, 2, 3, 4. So that's now, yeah, stupid implementation. Yeah, don't. This now should give something for K4, and should last maybe a few seconds longer. Okay, so for this one, conjecturally, it's divisible by 8. So what the program does is it successfully goes through the steps that so finds elements in the corresponding kernels, and then evaluates by the corresponding polylog and checks it against what one expects in terms of zeta values.
So what is conjectural here? Find out the other
Almost everything, yeah. So,
everything.
well, yeah. So, but the nice thing is that all these conjectures that, well, all the ones that we've checked so far, or been able to check, we have it. So Karim has this program on which proves K2. So the first one is compatible with his output. It's compatible, right? Okay, good. So and so it's even correct. Yeah, no, that would be embarrassing. And we can try even under GRH.
I'm not, well, I could prove it without GRH in that case, but the program does not do it.
Okay.
Currently.
Okay. Yeah. So with some qualifiers.
Okay, it's proven now without GRH.
Okay, without qualifiers, it's also so. So you get a picture that there are little programs that at least purport to get a decent conjecture on the size of the K groups, and some of them actually prove it. So that was essentially all I think that I wanted to present this morning. Yeah, thanks very much.
Are there any questions? Herbert?
For the Bloch-Wigner dialog,
Right.
just type polylog of m-1 with m equal 2, or does it require
A 3 in.
routine for dedicated continuation?
No, it only requires the flag 3 for the third parameter. So for the third argument, polylog, it's 2x3. So that's, or yeah, I think that's the standard one.
In a distant region.
Yeah. So this is a
Everywhere.
no, everywhere. So that's it. Huh?
I don't think the Paris implementation is able to evaluate everywhere.
Not the standard polylogs, but the Bloch-Wigner. So he asked for Bloch-Wigner, which is not an analytic function, but it's real analytic, and then extended to the singular points. Mm-hmm. Yeah.
Are you actually able to compute everything in your conjecture, to put everything together, and find that it works, find the lambda? Well, I guess you can always find the lambda.
Not well. I can get. I can get a conjectural one in each individual case. Now, what I presume is that for a given signature, we always get the same lambda, and it seems to be. So it certainly works for m equals 2, 3, 4. I've got a power of pi is clear. Power of pi is in front of the zeta star is pi to the m-1 times. In the times R1 plus R2 or R2 depending on the parity. So that factor is completely explicit. That was already Borel in his original statement where he related zeta f star, zeta f, and the K group lattices.
The rationals, I guess,
The rationals are the crucial thing. Yeah, yeah.
higher than numbers.
Not quite. For instance, this 131, 891, or whatever it was, that doesn't seem to come from anywhere, right? It's a degree field of the signature 2-2. So it doesn't come from Bernoulli in any form. I'm not in.
Find it.
You okay?